Welcome to part 3 of our equilibrium review, which will focus on Le Chatelier's principle, predicting which way a reaction at equilibrium will shift when either concentrations, pressure, or temperature are changed. In part 1 of this video series, we learned that chemical reactions are either irreversible or dynamic equilibriums. Recall also that a reaction is said to be at equilibrium when the concentrations of reactants and products do not change over time, as demonstrated when plotting concentration time data, or when the forward rate equals the reverse rate. If we stress a system at equilibrium, Le Chatelier's principle helps predict how the equilibrium will adjust to the stress. In other words, will the equilibrium shift toward products or shift back toward reactants to reestablish a new equilibrium? Stressing or disturbing the equilibrium is defined by either changing concentrations of reactants or products, changing the volume, which can also be considered to be a change in pressure, or changing the temperature. So let's first consider changes in concentrations to predict shift by examining an equilibrium we are already comfortable with, the Haber reaction. Le Chatelier's principle states, if you add more of a reactant or more of a product, the shift will be away from the addition, or if you remove reactant or remove product, the shift will be toward the removal. But we don't want to simply memorize these shifts, so let's deduce these shifts. At a certain temperature, equilibrium concentrations were measured and recorded in a 1-liter flask and an equilibrium constant calculated for this temperature. While at equilibrium, an additional 1 mole of nitrogen is added, raising the concentration of nitrogen. As we have already stated, equilibrium will be reestablished when the system shifts away from an increase. Let's mathematically prove this so we don't have to memorize direction of shift. So let's calculate the reaction quotient, abbreviated Q, using the new initial concentrations and compare Q to our known K value. Here, Q is less than K. Thus, we predict a shift to the right towards products, which equates to a decrease in reactant concentrations and an increase in product concentration. Remember, an easy way to predict shift with a Q value is to abstractly imagine that the Q value will strive to become the K value. In other words, the reaction will adjust to afford new equilibrium concentrations such that the K value is obtained. In fact, when final equilibrium concentrations were measured, the reactant concentrations did decrease and the product concentration did increase, which confirms our predicted shift toward product. And as a check, the known K value is obtained after the shift. We can also use the same type of logic to infer that if we add more product, it will shift towards reactants, away from the addition. For example, if an extra mole of NH3 is added to yield new pre-equilibrium concentrations, followed by a Q calculation, we see that Q is greater than K. Recall, the Q value will strive to become the K value, so a shift to the left, back to reactants, must take place, which equates to product concentration decreasing and reactant concentrations increasing. Now let's mathematically prove that if we lower the concentration of a reactant or of a product, the shift will be toward the removal. In this conceptual reaction, let's assume these equilibrium concentrations and calculate a K value for this temperature. If we remove some of product D, then using these new concentrations calculate a Q value, we see that Q is less than K. Thus, we predict a shift to the right will occur, toward the removal, so the Q value will strive to become the K value. Conversely, if we remove some of reactant A, then using these new concentrations calculate a Q value, we see that Q is greater than K. Thus, a shift toward reactants will occur, or we could say a shift toward the removal of reactant. Le Chatelier concepts can be employed to synthesize a desired product within an equilibrium by either adding a huge excess of one of the reactants, usually the cheaper one, or by removing one of the products as it is formed. These are important concepts for the synthesis of many desired products. For example, the synthesis of esters from a carboxylic acid and alcohol. One could add excess alcohol, which is typically the cheaper reactant, to drive the reaction to the right and form more of the desired ester. Or one could remove the water as it forms via a Dean-Stark trap, which will also drive the equilibrium to the right, to the desired ester. So let's examine one more equilibrium where we add a precipitating reagent to shift the equilibrium. For example, for the following equilibrium, one could add a solution of silver nitrate, which is the source for silver ions, to precipitate the thiocyanate ion as solid silver thiocyanate. By removing the thiocyanate ion from this equilibrium, the equilibrium will shift to the right. Or one could add a solution of sodium hydroxide, which is the source for hydroxide ions, to precipitate the iron 3 ion as solid iron 3 hydroxide. By removing the iron 3 ion from this equilibrium, the equilibrium will shift to the right. Thus, exploiting our knowledge of solubilities can also affect an equilibrium. We can also disrupt the dynamic equilibrium of gaseous particles by changing the pressure, which may be accomplished by changing the volume. For example, if the Haber reaction is at equilibrium and the volume of the reaction vessel is reduced, the pressure will increase. Le Chatelier's principle states the equilibrium will shift toward less moles of gas, towards products. Conversely, if the volume is expanded or pressure decreased, the equilibrium will shift toward the side with the greatest number of moles. But do we need to memorize this? Let's mathematically prove Le Chatelier's prediction. Here we have the Haber reaction in a 1 liter reaction vessel at equilibrium. Each particle of gas will represent 1 mole of each gas. Thus, the equilibrium concentrations are 4, 8, and 12 molar for nitrogen, hydrogen, and ammonia, respectively, and a K value can be calculated using these concentrations. If the volume is reduced to half a liter, then the new concentrations can be calculated as well as a Q value. The Q value is less than K, thus the equilibrium will shift to the right, causing a decrease in concentration of the reactants and an increase in concentration of ammonia. In fact, when the system reaches equilibrium in the half-liter reaction vessel, the reactant concentrations did decrease and the product concentration did increase, which matched the given K value. This result matches Le Chatelier's prediction that the system will shift toward less moles of gas when the volume is reduced or that the pressure is increased. One can also imagine the converse mathematical proof if the volume is doubled to 2 liters, which we can think of as a reduction in pressure, that the equilibrium will shift to the left, toward the side with more moles of gas. Calculating the new concentrations, followed by a Q calculation, where Q is greater than K, we prove that the equilibrium must shift to the left, as Le Chatelier's principle predicts. In summary, if the pressure is increased, the shift will be toward less moles of gas particles, and if the pressure is decreased, the shift will be toward more moles of gas particles. It is also worth noting that if an inert gas is added, there will be no shift in equilibrium. In this example, hydroiodic acid has the same number of moles on both sides of the equilibrium. Thus, if the pressure is increased or decreased, the equilibrium will not shift. To consider temperature changes, we have to include changes in enthalpy. The first equilibrium is exothermic and the second equilibrium is endothermic, as indicated by the negative and positive signs for delta H. For an exothermic reaction, energy is liberated. Thus, if we treat energy as a product, the equilibrium can be rewritten. Similarly, for an endothermic reaction, energy is required as a reactant. Thus, if we treat energy as a reactant, the equilibrium can also be rewritten. We have already demonstrated that an increase in concentration of product will cause the equilibrium to shift away from the increase. Thus, if we increase temperature or energy and treat energy like a product, there will be a shift away towards reactants, which will change the concentrations of reactants and products. These changes in concentrations will afford a new equilibrium constant, which is why equilibrium constants are unique for a given temperature. Conversely, we could lower the temperature, which equates to a removal of energy, and the shift will be toward the loss of energy, yielding new equilibrium concentrations and a new equilibrium constant for the lower temperature. Thus, for an exothermic reaction, if temperature is increased, there will be a shift to the left and a new smaller equilibrium constant will be obtained. If temperature is decreased, there will be a shift to the right and a new larger equilibrium constant will be obtained. For an endothermic reaction, if temperature is increased, there will be a shift to the right, changing the concentrations, and a new larger equilibrium constant will be obtained. If temperature is decreased, there will be a shift to the left, changing the concentrations, which affords a new, smaller equilibrium constant. Thus, for an endothermic reaction, if temperature is increased, there will be a shift to the right, and a new larger equilibrium constant will be obtained. If temperature is decreased, there will be a shift to the left, and a new, smaller equilibrium constant will be obtained.